All right, awesome. So I'd like to get this started by asking you all a question. How many of you all do offline batch processing of some sort? Okay, awesome. Well, I'm glad you all are here because today we're talking about how you can do faster and cheaper batch inference on Ray. So to get this started, we're going to be talking about what is batch inference and why you should care. Next, we'll talk about some of the challenges you might experience and what current solutions look like in the space. And in particular, we'll look at 3 solutions: SageMaker Batch Transform, Apache Spark, and Ray Data. Finally, we'll talk about some features that are only available on Anyscale, as well as some success stories.
Cool, so the first question is, what exactly is offline batch inference, right? So I think most of you guys, most of you raised your hands, so you probably already know, but just to rehash, it's ultimately a very simple workload, right? You have a large data set, consisting of terabytes or possibly petabytes of data. You have a pre-trained model, and what you want to do is take each data point you have, pass it through the pre-trained model to get a prediction. And optionally, you may have some pre-processing that you do before feeding in the data to the model. So overall, it seems like a very simple workload, but there's a few challenges really, particularly that we've seen when you actually want to scale this out. So scale this out to hundreds of GPUs and really a terabyte scale data. So let's go through some of these challenges. So the first one really is how you can manage your compute infrastructure. So when you're dealing with lots of data, obviously you need a lot of compute in order to efficiently process and do inference and all that data. So you need some system to be able to create clusters and create like GPU clusters for you. And in particular, you may need to manage heterogeneous compute infrastructure. And what this means is that if you have a cluster consisting of both GPU nodes and CPU nodes. So we'll go into a little bit more detail later about why this type of heterogeneous clusters can be useful for performance. But really, if your batch inference workload is bottlenecked on expensive CPU preprocessing or bottlenecked on bottlenecked on CPU RAM, you may want to add additional CPU-only nodes, which are cheaper than GPU nodes, to your cluster. So have a mix of both GPU plus CPU nodes. The second challenge is how you can actually utilize all the resources in this cluster. So once you have a system to create your clusters for you, how can you actually take your job and have it use all the resources? So making sure your GPUs are fully saturated, making sure your CPUs are utilized. The reason this is important, obviously, is because you want to make sure that when you're paying for this compute, you're using them, right? You don't want CPUs or GPUs sitting idly and not being used because you're paying for them. So for cost-effective batch processing or batch inference, you need to make sure you're utilizing the resources at any given point in time. Third, you want efficient data transfer from your storage, where you're saving your data, like S3, to CPU RAM, where you want to possibly do CPU preprocessing, and then to GPU RAM, where you actually do model inference. So again, having efficient data transfer is really important to maximize performance and making sure that you're fully saturating your GPUs. And the last challenge that we see is really on developer experience. So you don't go, right, when you're developing these types of processing pipelines, you don't go directly to production. You probably want to start off with working on a smaller data set and making sure your pipeline is working well. So you need a good developer experience so you can iterate quickly on a smaller data set during development and then have low friction when you move that code that you built during development over into production. So these are the 4 challenges that we see for what may be considered a simple workload like batch processing or batch inference, but becomes much more complex when you scale it out. So these are the 4 challenges that we see. So now let's go into what really does the industry recommend, right? So what is the best solution that people are recommending for addressing these 4 challenges? I think the best, this is one tweet that I saw about, so this is Ben Hammer, who's one of the creators for Kaggle. So you just pose this question on Twitter saying, I want to spin up a bunch of GPU spot instances to run batch inference jobs. What is everyone's favorite approach? And we can take a look at some of the responses to really see how the industry is thinking about this. Right? So the first response is just very definitively is just use AWS batch. You can use Modal Labs as one option. Lightning AI, like PyTorch Lightning, also saying they'll do offline batch processing. You can also roll out your own with your cloud vendor of choice. Someone's using Kubeflow. Someone's using Azure Batch Compute. This person's using Array Serve for offline batch inference. But overall, it's very disjoint set of solutions that people are looking into, right? Varying from using cloud vendor solutions to even just doing it yourself. So what we want to do is really categorize the different solutions that people are looking into or people have tried out for offline batch inference. And we've determined 3 different categories that the solutions fall into. So the first approach, or first category of solutions is what we call like batch services. So something like AWS Batch or GCP or Azure Batch. So how these work is that you can go to your cloud provider of choice, create a cluster, right? So you can request I want this many instances, and then the solution will like create the cluster for you, and then you can deploy your code or your software to run on these instances. So this partially handles challenge number one of being able to have like a managed infrastructure, so easily creating clusters. Some of these don't handle heterogeneous clusters, but it does partially handle challenge number one. But really, these solutions don't handle the remainder of the challenges, right? So developer experience is pretty not great when you're dealing directly with like EC2 instances, and in particular, the stuff about having efficient data transfer and utilizing your resources, that's all on you as the user to make sure that the software you are writing is properly processing your data in an efficient way and is actually utilizing the resources on these EC2 instances, for example. So these solutions really handle the managed infrastructure part, but they don't handle anything about the software aspect or how you can actually use or build an efficient data processing pipeline. Something like Modo Labs is another option. So they have a much nicer developer experience, but again, they don't have a software written necessarily for actually processing large amounts of data and making sure you're fully utilizing all the resources in your cluster. So this is the first category of solutions that we see, so batch services. The other category of solutions that people may also use for offline inference is actually just shoehorning an online inference solution for the offline case. So using something like BentoML or ArrayServe or SageMaker batch transform. So these solutions, they can abstract away infrastructure complexities. Most of them are pretty well integrated with the rest of the ML ecosystem, and they have good abstractions for model packaging. But the problem when you try to force in like an online inference solution to the offline case is that it can add like additional complexities, additional overhead for the offline case. So usually this includes things like starting up an HTTP server and sending requests over a network. Sometimes something like SageMaker batch transform has a max payload you can send for each request. So like these additional complexities really make it hard to saturate GPUs for what doesn't really need an HTTP server, right? You're not building an online application. So for something like offline batch inference or offline processing, these online solutions don't necessarily work well, to the point where even BentoML integrates with Spark as a backend for offline inference rather than using their existing backend for the offline inference case. And the third category of solutions that we see is distributed data systems. So these are things like Spark and Ray data. And these solutions are the ones that are actually well designed and well built to be able to process large data sets. So something like offline batch inference really is just a map operation. You have a pre-trained model and you just want to map that model over a bunch of data. So these are where distributed data processing systems really shine. So they can easily scale across your entire cluster. They have support for data partitioning and being able to batch your data effectively. And they have a really good built-in I/O layer, so you can connect the different data sources and load in data very quickly with these solutions. So these are the three categories of solutions that we generally see for offline batch inference, using just batch services, trying to use an online solution for the offline case, and then actually using distributed data systems. So let's take a look. We're going to do a deep dive into three candidates out of this entire solution space. So what we did is we actually ran like an image classification benchmark comparing SageMaker batch transform, Apache Spark, and Ray data. So the setup here is that we have a pre-trained ResNet 50 model, and we want to do batch inference on ImageNet data. So the pipeline is very simple. It's just you want to read images from S3. You want to do some simple CPU pre-processing, such as resizing, cropping, and normalizing those images. And finally, you want to do model inference on GPUs. And you run this on both 10 gigabytes and 300 gigabytes. So we can take a look at the results that we got. So we tried a few different Spark configurations, also SageMaker batch transform, and then finally with Ray data sets. So you can see that Ray data outperforms SageMaker batch transform quite considerably, and is also around 2 times faster, or 2 times more throughput than the best Spark configuration. So we can take a look at diving more deeply into kind of why we see Ray data having better performance than some of these other solutions for this type of workload. So first, about SageMaker batch transform. So this is one of the solutions that falls into category number 2, which is using online inference solutions for the offline case. So again, this addresses the challenge number 1 partially. It abstracts away the infrastructure management. But with regards to the rest of the challenges, it doesn't really work well. SageMaker batch transform uses an architecture for online serving. So it starts an HTTP server, deploys a model as an endpoint, and each image is sent as like one request to the server to get predictions back. There's also no support for batching across multiple files, and the max payload size for each request is 100 megabytes. So a lot of these additional complexities, which may benefit the online inference case, make it very hard to actually saturate GPUs on the offline case. For the offline case, if you have a bunch of data, you want to like make sure your batch sizes are large as possible. You don't want any payload limits when you're sending requests. So that's where we see that SageMaker batch transform is not having as good performance compared to like Spark or Ray data. Add to that SageMaker batch transform generally doesn't really have a good developer UX and more difficult to debug. So hard to iterate as quickly as you can with something like Spark or Ray data. So now let's take a look comparing Ray data and Spark. So really the differences here is that both can effectively scale out to many different GPUs across your entire cluster. But the difference here is really how you can actually utilize all the resources in the cluster effectively with both Ray data and Spark. And one of the key properties about offline batch inference workloads, especially for when you're working with deep learning models, is that they consist of both CPU and GPU processing. So you have some pre-processing steps that you do on CPU, and the actual model inference takes place on GPU. So you need to leverage both sets of hardware effectively for maximal performance. The key difference in performance here between Spark and Ray data is the underlying execution engine. So this GIF kind of explains the difference between Spark and Ray data. So Spark uses basically underneath how Spark works is that it uses a bulk-based execution. So both the CPU stage, the pre-processing, and the GPU stage, which is the model inference, are all fused together. So how it works is that you take your first two partitions of data, you pre-process them, then do inference, then save them, and only then do you start processing the next set of data. Ray data, on the other hand, has an underlying streaming-based execution engine. So if you came to one of the talks earlier today about Ray data or the talk yesterday about Ray data, it went into more detail about the streaming execution engine. But how it works is that it can effectively pipeline all your data across all the different resource types in your cluster. So while you're doing model inference on one set of batches, at the same time you can be doing pre-processing on the next set of batches. So you can effectively pipeline all your data through all the different operations because these operations are have different resource requirements. And in between these stages, you can buffer the data in the Ray shared memory object store. So as you can see, that Ray data is able to, because it's streaming the data throughout, it can basically has higher throughput. So you can process and then do inference on the data much faster than you can with Spark. The other advantage with this approach is that you can actually independently scale out each of the stages. So with Spark, your parallelism is limited by the number of GPUs in the cluster. But with the Ray data, you can scale out your CPU pre-processing independently from the GPU inference. So making sure you're actually fully utilizing all the resources in your cluster effectively. One of the other advantages that we have with the Ray data is that you can actually work with heterogeneous clusters. So this is very important for cases where your batch processing is bottlenecked on memory. So when you're working with things like images or videos or audios or a lot of the new type of unstructured data that we're seeing with newer AI workloads, these are bottlenecked on memory. So rather than adding additional GPU nodes, which are more expensive, if your bottleneck is on CPU memory, you can actually add CPU-only nodes to your Ray cluster and have a cluster consisting of both GPU and CPU nodes. So you can do pre-processing across the CPUs of your entire cluster, and then the intermediate data is buffered in the shared memory object store. And then when it's time for inference, some of the nodes don't have GPUs, some of them are only CPUs, but Ray can handle that effectively, and will move all the data from all the pre-processed data to the appropriate nodes in order to do inference. So this way we can effectively overcome our memory bottlenecks without needing to spend more money to get GPU nodes. You can do it with CPU-only nodes. So that was challenge number 2 on how you can effectively utilize all resources in your cluster for hybrid CPU plus GPU workloads. Challenge number 3 is how you can actually do efficient data transfer. And the key property of this workload is that we're working with multi-dimensional tensors. So again, with something like images, unlike tabular data, each image is represented as a large multi-dimensional tensor. And this is where something like Ray data really shines because it's basically essentially built entirely on NumPy plus PyArrow. So something like the JVM to PyArrow overhead, you don't get that overhead when you're working with the fully Python-based system like Ray Data. And there's no pandas involved, which incurs a copy between PyArrow to pandas. So with Ray Data, you can entirely work with NumPy and PyArrow, which are built for tensors. And then finally, this fourth challenge is on developer experience. I think one of the advantages Ray Data has here is that it's fully Python native, so you get better stack traces. And a lot of the basic debugging techniques that you use for Python continue to work with Ray Data. So that was for 10 gigabytes. Let's take a look at 300 gigabytes. And this one, we can do this live. So I'll have a side-by-side here of Spark versus Ray Data. And then we can take a look at this. OK, I think you guys can see this, hopefully. So on the left-hand side, we have Ray running on the Anyscale platform. And then on the right side, we have Spark running on Databricks. And so again, this is the same workload that we talked about, image classification. So 3 steps is that 1, we want to read images from S3. 2, we want to do pre-processing on CPU. And 3, we want to do model inference on GPU. So I'm going to run both of these right now, and then we can take a look at the throughput once they finish. So this is the Ray Data code. So as you can see, we want to use like the Ray Data streaming executor, and we have these images stored in S3 bucket. So there's a single line to read those images, which are stored as Parquet files, into a data set. Then we define our pre-processing function, which does resizing, cropping, and normalization, and then map that pre-processing function over the images that we read from S3. Finally, we define a class where we actually do our inference. So as part of the state of the class, we load in a pre-trained model, and then we can do inference on batches, just passing the batches through the model to get predictions. And because we have 16 GPUs in our cluster, we can specify that we want to use 16 GPUs, and we stitch the entire thing as a Ray Data pipeline. So as you can see, it's churning away, concurrently doing both the pre-processing on CPUs as well as the inference on GPUs. So now we can go to the Spark side, which the workload is pretty much exactly the same. So again, here is first thing we want to do is we want to load in our pre-trained model. So we load in the pre-trained model and then broadcast that to all the Spark workers. Then we read the same exact bucket from S3 to load in our images. We define a pre-processing function. It's a little bit more complex because Spark doesn't have native support for multi-dimensional tensors. So you have to flatten the tensors and unflatten them as needed. Then we do our prediction, which again is just passing our data through the pre-trained model and then getting the prediction results back. So you're going to put this all together in a Spark pipeline, essentially, and then run the whole thing. So as you can see, with Ray Data, we're getting around 3,000 images per second. I'm going to skip to the end here for Spark. And then we see we're getting like 684 images per second with Spark. So 300 gigabytes across 16 GPUs. We're getting much better performance with Ray Data. And this is primarily because what we talked about, that Ray Data uses a streaming execution backend, which is really gets you much better performance for these hybrid CPU plus GPU workloads compared to something like Spark, which is all bulk-based. Okay, sorry. Yeah, and then so let's see how Ray Data scales up to 10 terabytes. So we talked about 10 gigabytes, 300 gigabytes, and 10 terabytes. Again, we're using a 40 GPU cluster, and we're getting over 90% GPU utilization throughout the entire run. So we really are saturating our GPUs pretty and almost close to maximal as we can get. And in this case, we are using heterogeneous cluster, so a mix of CPUs plus GPUs to better improve our performance. So just to summarize a comparison between SageMaker Batch Transform, Spark, and Ray Data, and across the 4 different dimensions of the challenges that we see for large-scale batch processing. So all 3 of them can really help with managing your compute infrastructure. But when you want efficient resource utilization and efficient data transfer, specifically for these hybrid workloads, and also when you're working with unstructured data, Ray Data really gets you the best performance there. Plus, it's like fully Python native, so developer user experience is much better. The same code that you can work with on a smaller scale can then easily be transferred to when you're actually moving this to production at a large scale.
Cool. So Amog just told you about how Ray Data performs for image classification. Now, I'd like to tell you about how Ray Data performs for stable diffusion, and in particular, also how it compares against Spark. To understand this, we ran a benchmark with 16 GPUs and 300 gigabytes of data. This corresponds to about 500,000 images. What we found is that Ray data performs almost 1.5 times faster than Spark. Can we do better than this? Probably not. What we found is that we achieve nearly 100% GPU utilization on this task.
Cool, so now we saw where offline batch inference is important for both image classification as well as a newer type of workload for image generation with stable diffusion. How does offline batch inference work for LLM application development, for example? It's a pretty critical piece, and in particular, really where it's most useful is when you're scaling embedding pipelines for RAG applications. So if you're not familiar with RAG applications, the way it works is that you want to build, for example, a Q&A system over a set of data that you have. You process that data, you embed that data, and store it in some vector database. Then when a query comes in, like a user question comes in, you can look at the embedding similarity between the user's question as well as your data to pull in the relevant context to feed it to your LLM, which will then produce a response back to the user. But the first part of this really is just a batch inference problem. You have a bunch of data, a bunch of documents. You need to do some processing on CPU to split them and chunk them, and then you need to embed them, which means doing inference with the embedding model on GPU. So using Ray data can really help scale out this entire process and make it run much faster. So something that would take several hours, like if you have a bunch of PDFs and you're just indexing them one by one, can now be done several minutes by indexing them in parallel. So if you want to build LLM applications that are very real time, or you have data that's often changing and you need to keep on indexing them as they change, you want to make sure that indexing pipeline can run very fast and very efficiently.
Cool. So hopefully we've convinced you now that open source Ray data is a great solution for offline batch processing. Now I'd like to tell you about some features that are coming only to Anyscale. We've seen an increasing number of users work with unstructured data like video and audio. So we've introduced APIs specifically for streaming this sort of data. In addition, cost continues to be a concern for our users. So we're enabling Spot instance support by default on Anyscale. First, let me tell you about the video support feature and what sort of performance you can expect to get. Here's what the API looks like. The Video Data Source API lets you stream from cloud storage or local disk in a streaming fashion. To understand the performance, we ran a benchmark with 100 GPUs and almost 1,000 hours of footage. In comparison to running this on a single machine, you can run your entire batch inference job in just 4 hours. Can you do better? Almost not. You can get almost 100% GPU utilization, again, with this video object detection task. Next, I'd like to tell you about the audio support feature. Similar to the Video Data Source API, we've introduced an audio data source class. This lets you stream data, again, from cloud storage or local disk. What sort of performance can you get? We ran a similar benchmark with 100 GPUs and 1 terabyte of audio data. In order to transcribe this data using OpenAI Whisper, it just took less than 1 hour. What sort of GPU utilization can you expect? About 60%. This might not look great, but if you run the same model in a loop on a single machine, you see that you get almost as good of GPU utilization as you can possibly get. Finally, I'd like to tell you about Spot instance support on Anyscale. Ray data is fault tolerant, and this means that you can use Spot instances. What sort of cost savings can you expect to achieve? Remember the video benchmark I told you about? With open source Ray, this benchmark would cost $500 to run, whereas with Spot instances on Anyscale, the AWS cost is only $192.
Cool, so you went over why offline batch inference is important, how it's a critical workload, and went over some of the candidate solutions for doing high-performant offline batch inference. For both image classification and for generative AI, talked about LLM applications, and Balaji went over some of the additional features we have in Anyscale. I think I'm going to wrap this up with some case studies that we've seen for people using Ray and using Anyscale for offline batch inference and some of the value they get out of what we talked about today. So the first one is ByteDance, which is the creators of TikTok. So their use case is really, really cool and very advanced. So they have 200 terabytes of both image and text data, and they want to pass both of them in through a model to generate embeddings in the same embedding space for both the images and text data. One of the key characteristics about this workload is the model doesn't fit on a single GPU, right? So they have to shard the model across multiple GPUs. And they actually chose Ray data over Spark for this type of workload because of Ray data's expressivity and its performance. So with the Ray data, you can simply easily create this pipeline where you're doing reading, pre-processing of your data, passing the data through the first stage, which is the first few layers of the model, then to the second stage, and then to the third stage, each of these stages consisting some layers in the model, and then finally writing it out to a data source. So with Ray data, you can actually stream this entire pipeline. So data can be streamed all the way through across all the different model stages versus something like Spark. That's not the case. So another use case we want to talk about is a company called Sewer AI, which what they do is they basically send robots into like sewers to analyze damage or any other problems that may be occurring in sewer pipelines. So they have a bunch of videos, like thousands of videos that they want to process frequently. And then do like object detection on different frames of the video. So previously they were using SageMaker. Instead they adopted Ray and Anyscale, and they see around 75% cost reduction in their offline batch inference workload when using Ray and Anyscale.
Cool. So to wrap this up, here's what we talked about. Batch inference is a critical workload, especially for emerging applications like generative AI and LLMs. And hopefully, we've convinced you that Ray data is the best open source solution to batch inference for developer productivity, cost, and performance. And finally, we're introducing new features on Anyscale to further enhance batch inference. And the take-home message here is that if you want faster and cheaper batch inference, get in touch with us. Thank you.
Okay, maybe have one question.
How does Ray handle fault tolerance, like if you're 2 hours into that 4-hour-long job? Oh, hello. My question is about fault tolerance. So if you're halfway through one of those really big jobs, I haven't used Ray that much, so maybe it's a really simple answer, but how does it handle basically like something failed really drastically and you need to restart the job? Can you pick up where you left off? Are there like checkpoints? Or is that totally dependent on exactly the program you wrote? So sorry for the somewhat vague question.
Yeah, no, it's a great question. So you don't have to restart the job from the very beginning, right? So Ray has basically built in object reconstruction. So if a node fails and there's some data or some state that the node is holding, what we can do is we can actually regenerate those objects. So if you lose some of your intermediate data, we can rerun the pre-processing steps for just that data that you lost. So if you're basically for any data that's totally fine and not touched by any node failure, that data is all there. So you don't have to restart from the very beginning. You can essentially only reconstruct the data that's lost on a node failure.
Okay, another round of applause for Aimok and Balaji. Thank you so much.